This is part 3 of vector representations. So let's now discuss an example in the vector space of polynomials of degree 2. Okay, so P sub 2 is a vector space of polynomials of degree 2. Remember, if we say something like W is a member of P sub 2, well, what we mean is that W could be expressed as something that looks like C plus BX plus AX squared. Maybe I'm writing this in the backward sense as we usually do, but that's what we mean, right? So this is a polynomial with variable x and coefficients a for the leading power, b for power x to the 1, and c for power x to the 0, which is 1. So here's a specific case of a member of P sub 2. We call this a vector given that P sub 2 is a vector space, and so members of vector spaces in general are called vectors. And we're going to consider the following. We want to come up with a representation of this vector u of this polynomial relative to one basis, and then maybe we can explore relative to another basis. Okay, so let's see. So we say u is this polynomial of degree 2. It has coefficients and well, it has u is 15 plus 10x minus 6x squared. So let's consider what is known as the standard basis for polynomials of degree 2. Okay, so now this set B contains the quantities 1x and x squared. This one really is x to the 0. Okay, but so we could represent that arbitrary member of P sub 2 as a linear combination of these basis elements, right? So this is kind of related to what we did before with the standard unit vectors E1, E2, etc., right? So we could represent one vector easily, almost by inspection, using the standard unit vectors. But here, you can think of these quantities as the standard basis elements. This is a very nice basis for P sub 2. So writing this polynomial in terms of these basis elements is straightforward. 15 times x to the 0, 10 times x to the 1, and minus 6 times x to the 2. So this is going to lead to a straightforward vector representation, this row operator of u being this polynomial, okay, vector operator row of u at b, where b is given by these bases. We collect these coefficients 15, 10, and minus 6, and that's what they're being stored here on this column vector. But so what happens now if we consider a different basis, a different set that is linearly independent and spanning? So this set C has the property that the span of C is exactly equal to the vector space of polynomials of degree 2. Now, what we would like to do is to find scalars, here called a sub 1, a sub 2, and a sub 3, such that we could represent, remember, I guess what is at stake here, this is U, and the question is U being a member of the span of C, and therefore can we, well, not equal sign here, but therefore can we write U as A1, so I'm going to call these things, I'm going to give them a name. This would be V1, and this here would be V sub 2, and this one here would be V sub 3. So we want to represent U as A1, V1, A2, V2, and A3, V3. So we would like to find such values so that U can be expressed exactly as this sum, that U be equal to A1 times 1, A2 times 1 plus x, and A3 times V3, which is 1 plus x squared. So that's what we have here. And so what happens if we multiply this? This becomes A sub 2 plus A sub 2x. And if we do this product here, then we have A3 plus A3x plus A3x squared. So everything is adding up. So this is A1 plus A2. We could even group things here. So things that don't have x, here is A1 and A2. And things that have x, say this is A2 here, and that is A3. And maybe I'm leaving behind this A sub 3, so maybe I should have written A sub 3 there. And then things with x squared would be A3 times x squared. So what we do now is that equality on P sub 2, we're equating two things. So the thing without with coefficient, the coefficients are x to the 0. So that would give us something that looks like 15 equals A1 plus A2 plus A3, right? So I'm taking these three quantities, adding them up, and they're equated to, we have one polynomial on the left-hand side, another polynomial on the right-hand side. Things with x, that would be 10 equal to, we're equating the coefficients, so this is A2 plus A3, and then minus 6 would be equal to A sub 3. So in other words, we could come up with this linear system. The scalars A1, A2, and A3 are the unknowns, but you could form the augmented matrix, do a calculation of solution set. You could also do back substitution. If A3 is minus 6, you could substitute this quantity for the quantity minus 6 and then move that. And so the thing is that you would find values for A1, A2, and A3 either by calculation of solution set or by using back substitution. And then, so in other words, we put those values stored into a column. So this is 5, 16, and minus 6. Those are precisely the values needed to write A1 V1, A2 V2, and A3 V3, right? If we want to use those basis elements, V1, V2, and V3, we use these coefficients in that linear combination, and that's precisely what would give the combination being the confirmation that U is indeed, with these coefficients, U is a member of the span of C, right? And so we have a name for that, the rho operator. So now rho of U relative to that basis C is something that looks like 5, 16, and minus 6. So let's now consider a different basis of P sub 2. I have been using V1, so now let's think of this first polynomial here, maybe like W1, and this one would be W2, and this other one would be W3. So this set D containing these three polynomials we need to do a verification of linear independence, okay, and of the spanning property. But what we want really ultimately is to find values for A1, A2, and A3 such that we could write U as a linear combination, right? So we're saying we would like to express U as a linear combination A1 W1, A2 W2, and A3 W3. So here on the right-hand side, I have the linear combination involving the members of the set D with coefficients A1, A2, and A3. This is a very similar calculation. We're going to multiply these coefficients by these basis elements, and we're going to have one polynomial of degree 2 on the left-hand side of this equation. This is equality, right? This is the definition of things being equal, equality in P sub 2, and then we have another polynomial of degree 2 on the right-hand side, and we equate the coefficients. So that would lead to this system, this linear system of equations. We could form the augmented matrix, right? This is something in which we would have the last column would be 15, 10, and minus 6. But then the other columns now have first column minus 2, minus 1, 3, 1. There's no A2 term here in the second equation, so 1, 0. And there is a minus 2 on the last equation. And then the last column, column number 3 would have 5, 4, and 1. I hope that I did this correctly, right? So first column has the numbers minus 2, minus 1, and 3. Minus 2, minus 1, and 3. Column 2, we have to know that the second equation has A2 doesn't appear there, so usually we take care of that by saying 0 times A2. That's the 0 in that second column. So we have 1, 0, minus 2. That's what we have here in the second column. And then we have 5, 4, and 1. 5, 4, and 1. We form this augmented matrix. We row reduce and calculate the solution set for this system of linear equations. There are equations in A sub 1, A sub 2, A sub 3. And then by doing that, we can find that values of A1, A2, and A3 are these values stored here, minus 2, 1, and 2. With those values, we could represent U in terms of that basis set D.